dans son rétroviseur, mais elle n'a jamais. Quand elle ne le voit pas un matin, elle s'inquiète, comme s'il lui appartenait un peu dans sa tête. Elle n'a jamais, ne serait-ce que baissé sa fenêtre. Il ne s'en rend même pas compte à croire qu'il est bête.
Hello and welcome to the video on line integrals. So in this video, we'll be going over, or it might be broken up into two, but basically there are two types of integrals over curves. So two types of integrals over curves. And they are, the first one are scalar line integrals, and sometimes they're called path integrals, but the most common usage is line integrals. So there's scalar kind and there's vector line integrals. And we'll be going over both shortly. So we're going to start with scalar line integrals. So what they are, so scalar line integrals are integrals of functions, basically. So integrals of functions. Alright, so let's say we have some curve, right? I'll just make it like a curve like that, okay? So we have some curve here, and basically what we're going to be doing is there's some function that you're going to be given, and let's say it's of function of something. So you're going to be given a function, so given function, right? So given an f, and then basically at each point, your f takes a certain value, right? And what the scalar line integral does is it adds up all of those values along your way, along your path, okay? So let's say we have this long path here, and we're kind of going to do what we've done before with integrals, and we're going to apply like Riemann sums, and break it up into little intervals. Okay, so right now I'm breaking it up into little sub-intervals. Okay, so this first curve here, this first curve is called C1, this one's called C2, C3, and etc. And you can break it up into infinitely many, up to a Cn. So Cn curve here. Alright? So the long curve, like the whole thing, is made up of C1 plus C2 plus C3 all the way up to Cn. Okay? So now what we're going to do with this interval, because you can't just break something into sub-intervals and then not do anything with it, because if it just sits there, then it's just going to sit there. But what we're going to do now is pick sample points. So what we're going to do is pick a sample point, and we'll call it P1, because it's in curve 1. The sample point in here is called P2, this one's called P3, etc., 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 and this one's called P sub n. Okay? So what P is a sample point on your curve in sub-interval, or we'll call it like a curve segment. Okay, so basically, what happens when you take when you break it up like this is that your sum, your total sum, this may look familiar from Riemann sums, but I equals 1 up to n, so I just tells you which number little curve that you're on, and then the sum of this of your f, so this is your given f again, and this is a function that depends on your point, like where you are on the curve, okay? So the function evaluated at your sample point, and then times the length of your little curve times the length of c sub I. Okay, so in this case, as I said, length of c sub I is equal to, their notation is like this, delta of s sub I. So s, sorry, too many arrows, but s represents your arc length. So in this case, your little arc length, right? So length of c sub 1 in this case would be the length of this curve. Okay, so basically what this is saying is that, disregard this for now, but you're going to take your function, whatever that is given to you, and then you take a point within that. So you pick a point inside your little curve, and you evaluate the function at that point. So function evaluated at pi, and then we have, so we're going to take the value of the function there, and then we're just going to multiply it times the length of the little curve. Okay, and we're just going to do this, and what this part means is that we're going to do this at all of the little curves and then add them all up. Okay, so then we just get a total value for the whole curve. Okay, so what this is, so this turns into, I'll move on to the next slide. So what this is we want, so I'll redraw the curve real quick here. So here's our intervals here, something like that, right? And then we said that the length of a small curve is our delta S sub I. Okay, so and this was like the arc length of our little curve. So what we want essentially is that S sub I goes to 0. Because then that would mean that our subintervals, or our little curves, would be really tiny, right? And remember, that's what we did in Riemann sums as well. We wanted the subintervals to go to, the number of them to go to infinity. So the same concept is here. We just want the arc length to go to 0 of each little curve. Okay, so this is equal to the line integral, because that's what we're interested in. So you're given f of xyz ds. This is the notation. So this represents a line integral, a scalar line integral, is equal to the limit as this thing goes to 0, as delta S sub I goes to 0, of the sum that I just wrote on the previous slide. So we're going to have this, and f of p sub I times delta S sub I. Okay? So what this is, now from here, given this, then we can, let's look at this a little bit more in detail. So what this is, as I said before, this is basically your arc length. Okay, so arc length. And what the arc length formula tells us is that this delta S sub I should be equal to the integral of, from a to b, so it's start and end. Let's say a and b is here. This is our t sub I minus 1 and t sub I. Don't worry about the notation here. It's not, honestly, this part isn't really like super important as far as solving problems, but it's important for your understanding of the concept behind why the formulas work as they do. So anyway, so basically this is the start point of your little interval, and this is the end point of the little curve. So here's your start point, and here's your ending point. Okay, this is the formula for arc length, and this will be the magnitude of your c prime of t dt. And now you might be wondering, like, what's c now? I don't know where that comes from. But this is when I'll say what t is. So c of t, this is a vector. And so when c of t is equal to the following: x of t, y of t, and z of t. So at this point you might recognize this as a parameterization, and it is when this is the, or a, I'll just say a, because you can have multiple parameterizations, is a parameterization of the curve being, and I'll say studied, being studied. Okay, all right. So basically what this is, c prime of t is equal to, well, I'll write it on the next slide. What c prime of t is the, as I said, the magnitude or the length of the tangent vector, basically, essentially. So what that is going to be the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. Okay? So going back to the arc length formula, so we have delta S sub I, so that's the arc length of our really tiny curve, and this is going from t sub I minus 1 and t sub I. Don't worry, those are just the start and end points of the little curve. And then so this thing here, what I wrote before, is going to be equal approximately to c prime of t sub I, the magnitude of that, and then times delta t sub I. So as I said before, don't worry about this too much. I'm just providing it here for explanation. And if you need more, or if you want to look at it longer, it's also in your book as well. So anyways, going back to the entire formula, not just this s sub I, but the important part here, the part that you should take away, is that, just get rid of this like middle thing here, but delta s sub I is approximately equal to the magnitude of the tangent vector at your point, and then times the change in, or delta t sub I. So basically, we're just going to plug this back into our formula. So what we had before was the following. So we had this sum here, and then a scalar function f evaluated at your point on your little curve, times delta s sub I. So now what I'm going to do is equal it, or set it equal to, it's going to become something like this, and then we have, so p sub I, this is our point on a curve, so point on curve, right? Point on curve, but now our curve is parametrized, so now we have c of t, okay? So now that it's c of t, we can kind of word it like that. We'll just plug that back in here. So then we have our scalar function at some c of t. That just means a point on our curve, same thing, right? Now we just have another name for it, another parameterization, okay? So c of t, and then this is multiplied times, and we're going to use this relation here. So we're going to plug that in this spot. So then we have it times magnitude of c prime of t sub I, magnitude, and then delta t sub I. Okay? So, we're going to get a move on here, and I'll just write the final result, basically. Oh, also, just because it's good to know, this is another like variation of the Riemann sum, or an application of it. So, yeah, good to know. Alright, so this is a Riemann sum because we're adding stuff up, like sum, right? And it converges to the following. It's going to be A to B, and okay, I'll note it in the next thing I write, but f of c of t times magnitude of c prime of t, whoop, and then dt, where c of t is your parameterization, and t goes from A to B. Okay, so that's where the bounds come from, because everything basically depends on the curve here. Okay, so alright, yeah, so that's basically it. I'll write it, let's see, this is pretty formal notation here. And then also, it's good to note that f of x, y, z, so your scalar function, right, so this is a scalar, not a vector function, but a scalar one. So that and c prime of t must be continuous. If they're not continuous, then it doesn't hold. So these must be continuous. Okay, and then the final thing here, so what this is your scalar line integral. So another way to put that is your integral over c, so this is your curve, right? And then f of x comma y comma z, so this is your scalar function, and they just denote it ds for some reason. So anyways, but this is the ultimate equation that we were trying to get to. Alright, so now let's do an example. So we have example, calculate, and we'll do, so the same thing. So this just means calculate the scalar line integral, where, and then they'll give you sufficient information to solve the problem, of course, where curve C is represented by c of t equals cosine t, sine t, and t. So this is three-dimensional, right? And then also our f of x comma y comma z equals 1, right? So this is our scalar function here, f. And then c of t, it'll also tell you the bounds, the a and b, right? So in this case, in this problem, it tells us that t goes from 0 to pi, okay? All right, so this is our a and our b, basically. So first of all, what we want to find out is what is c prime of t, the magnitude. What is that equal to? That's usually the important part here in scale. Well, each part is important, each component, but I usually start with this for some reason. So anyway, so what you do is you just take the derivative of the c of t function. So then we get the derivative of cosine is negative sine, of course, and then derivative of sine is cosine, and derivative of t is just 1. So then we want to take the magnitude of it. So what that would be is basically squaring each thing individually, and then adding them together, and then square rooting. So what we have is negative sine t, and we're going to square everything, add it to the next component, squared, and add it to the final component, squared, and then we're going to square root the whole thing. Okay? So what we get is this is actually sine plus cosine, so sine t plus cosine squared t plus 1. Okay? And this turns into a 1, of course. So then we basically get that the magnitude of c prime of t is going to equal square root of 1 plus 1, which is square root of 2. Alright, so we have that part, so that's pretty simple. That's good. And now we have to look at the formula. So our formula, again, for the scalar line integral is from a to b, and these are our bounds for t of our parametrized curve. Okay, so it goes from a to b, and then the rest of the formula reads the scalar function with c of t plugged into it, and then times the magnitude of c prime of t, and then dt at the end. So we have this part here, and now we just need to plug this in. Okay, I'll continue this on the next slide so we have more room. So what we left off with was from a to b, and then f of c of t times the magnitude of this, or the length of that, dt. So we know that this equals radical 2. We just solved for that. And we know that f of x comma y comma z was equal to 1, right? That was a given. And we also know that from a to b is 0 to pi. Okay, so what we're going to do now is just plug everything in, and what we get is 0 to pi. Sorry, it's not 2 pi. That is a pi. And then we plug in 1 for here, because we can't plug in a c of t, even though our c of t was equal to cosine t, sine t, and then t. There's nothing, because this is our x, our y, and our z, but there are no x, y's, or z's to plug these in. So we're just going to stick with the 1, and then we have times our radical 2 dt, and then we just solve from here. So what we get is radical 2, and then a t comes in from integration, as t goes from 0 up to pi. So then when we evaluate this, we just get radical 2, and then pi minus 0, which turns out to just be pi times radical 2. Okay, so this is the answer for our scalar line integral. Okay. All right, and another thing I want to note, I'll do it on the next slide as well. So because our function, our given scalar function, was equal to 1, right? Remember how I said there was no x, y, or z to plug in, really? With the parametrized things, but because it's just a 1. So what this is basically, when we put everything together, is our f of x, y, z equaling 1, that was just 1 times the magnitude of the derivative of c of t times dt, and this should look familiar because this gives us length of, or arc length, I'll put that in, gives us the arc length of the parametrized curve from A to B. Okay? So anyways, that's just an important like special case, I guess you could consider it. So this is special when our scalar function equals 1. Alright? So that wraps it up for scalar line integrals. Now we'll be going on to vector line integrals.
Les choses se